Okay, let me walk you through this problem here. It's a great application of all the things we've been talking about with exponential growth and how it can affect retirement fund. So Rachel deposits $200 into her retirement plan each month, and the company also, so that's a keyword, also deposits half of her monthly deposits. So if she deposits $200, then the monthly deposits are going to be $300, because they'll put it in 100. So I'm going to label P as $300 a month. When you're doing a formula problem like this, it's always good to set up what each letter stands for in here. So her plan earns 6% per year, but it's compounded monthly, so the interest rate per period, because it's compounded monthly, so every period, every month, it's 0.005. So that's going to be our R. R is 0.005. And she wants to retire in 30 years. So that's going to play into the N, because N stands for the number of payment periods. So N is not 30 because she doesn't pay once a year. If she paid once a year, N would be 30, but she's paying 12 times a year for 30 years. So N is 12 times 30, so N is 360. And that's all the letters we need. A is the future value, so that's the amount we're trying to solve for. How much will she have when she retires? So we'll say, okay, now let's put it in the formula. A equals 300, that's our P. 1 plus R is 0.005. That 1 plus 0.005 is all raised to the 360 power. And then we're going to minus 1, and it's all going to be divided by 0.005. And, I mean, in future math classes, you might go into where this formula comes from. You don't really need to worry about that today. Okay, so let's see. That, after we round that, if you type that in your calculator correctly, you should get about 301,356. Give or take a couple dollars depending on when you rounded. So that's how much you would have after 30 years. Hopefully that makes sense. Going down here to the second part, now she would have 597,447 in her retirement account if she decides to retire in 40 years versus 30 years. So this amount up here is in 30 years. So let's say she started saving when she was 30 years old and she retired when she was 60. Well, this amount is 40 years instead of 30. So maybe she started saving earlier when she was in her 20s and then she retired when she was 60. So this is showing you how much more you could earn just with an extra 10 years of compounding interest. So how much more, how much extra does she have from the 40 years versus the 30 years? We would just subtract these two. So 597,447 minus 301,356. She would have $296,091. Wow, that's a lot of money extra just with 10 years time. And you might think, well, she deposited more because she was depositing, $300 a month for 10 years. Extra years makes sense she'd have more, but not that much more, because this goes on to say, oh yeah, well, she was depositing, but she only deposited $36,000 because she deposited $300 a month per month. Oops, $300 per month. That's really sloppy. For 10 years. So she deposited 10 years. So 300 times 10 years and 12 months in a year. So she only deposited $36,000. Where did all the extra come from? In pure interest, then, we would subtract $36,000 from this extra amount, $36,000. She earned in pure interest, just those extra 10 years, $260,091 about. So starting early to save for retirement really pays off because your money has a lot more time to compound. And that's the whole point of this project or this little assignment was helping you notice how much of a difference time makes in your retirement. Not only does the amount of money you put in make a big difference, I think everyone realizes that the money you put in makes a big difference, but a lot of people don't realize that the variable of time also makes as big, if not a bigger difference than even what you put in or what interest rate you're getting. So I hope that is more clear. If you didn't get it when you did the assignment the first time, maybe work through it one more time and see for yourself if you can do those problems. Thanks.